Now I'm going to group everything that we've explored so far into one gigantic table, and we're going to tie it all together. Okay, so up here I've listed all of the transformations we've discussed so far, and remember that we've been always talking about a point in 2 dimensions, a point in the Cartesian plane. Okay, but whatever you can do to a point, you can do to anything in the plane. So a line or a shape, an object, anything. Okay. So when we talked about a reflection in the x-axis, we saw that this was the transformation that occurred. Okay, so the x-coordinate moves to the x-coordinate, and the y-coordinate moves to the negative y. Okay, so this is the transformation that happens when you reflect a point in the x-axis. You can think about it like this, it means the same thing. xy goes to x minus y. Okay? Same thing with the reflection in the y-axis. You have the point xy goes to the point minus xy. That's the relevant transformation. Okay, a reflection in the origin takes x to minus x and y to minus y. Okay, and if you remember, that is equivalent to a reflection in the origin is equivalent to a rotation of 180 degrees. Okay, so these two are equivalent transformations. A rotation now, a rotation of 90 degrees, takes the point xy to minus yx. So you can see it hasn't just changed the sign on the x and the y, but it's actually flipped them. It's moved what was the y coordinate to the x position, and what was the x coordinate to the y position. A rotation of 270 degrees, okay, takes the point xy to the point y minus x. Again, a mixing. The rotation transformation through an arbitrary angle theta, okay, or I should say an arbitrary angle beta was the original notation. Okay, it takes x to cosine beta x minus sine beta y, and it takes y to sine beta x plus cosine beta y. This is an active transformation, okay, or an active rotation. So xy goes to cosine bx minus sine beta y, comma sine beta x plus cosine beta y. But you can see in this that the x coordinate moves to a new position that depends not just on the original x coordinate but also on the original y coordinate. That's really important. Okay, and then finally, we didn't exactly look at this in detail, but it's very simple to see. This is a scaling transformation. It just takes x to k times x, so some number k times x, and y goes to k times y. So k could be a whole number or a decimal or anything, so it could be a scaling up or a scaling down. So xy goes to kx comma ky. Okay, but remember that all of these transformations, you could do several of them at the same time. Okay, so you could combine a reflection in the x-axis with a rotation of 90 and then a scaling transformation, for example. So you can get all sorts of combinations, right? But if you look at each of these transformations, you can see that we can write in general, okay, we can write in general that x, okay, is transformed to a new position, sum a times x plus sum b times y. And y gets transformed to some new position, c times the original x plus d times the original y coordinate. Okay, this is how you write the most general case. So for example, I won't go through them all, but you can see that if, for example, you take reflection in the x, here x goes to x. So in that case, a is 1 and b is 0. And y moves to minus y. So in that case, c is 0 and d is minus 1. Okay, so you can choose different values that can go into these coefficients a, b, c, and d to spit out each of these different transformations. And this is the most general case. Okay, and this has a special name, in fact. Okay, any transformation that takes x and gives out some combination of ax plus by, and any transformation that takes y and gives some combination of the original x and the original y, like this, it's called a linear transformation. Okay, it's called a linear transformation because what's involved is just the original two coordinates. Okay, the new coordinates involve only the original two coordinates, and there's no powers. So, for example, it's not ax squared or ax cubed. Okay, there are no strange functions involved like sine or log or anything. It's just a simple linear transformation. Okay, so x gets mapped to some combination of the original xy, and y gets mapped to some linear combination of the original x and y. Okay, and what this in essence means geometrically is that any lines that you have in the original coordinates, they will be transformed into lines in the new coordinates. And these lines will stay parallel. If they're parallel in the original, they'll stay parallel in the transformed situation. Okay, so that is a linear transformation. And that's what we've been discussing so far is, in general, linear transformations. And this idea of a linear transformation will take us next into linear algebra, which is a very important and very powerful tool in mathematics and physics.